Here's a very nice problem on electron configuration of atoms. It covers pretty much everything you need to know about writing the electron configurations. That's why I chose Rubidium. And it says write the complete and abbreviated electron configuration for the highlighted elements. So I'm going to go all the way back down to this Rubidium, and we're going to do that and write it and see how it's done. Well, let's pull up a periodic table because that's going to help us quite a bit. Here I've got rubidium circled. It's an alkali metal. It's right after potassium. You don't see much of it used in terms of chemistry. Potassium is used quite a bit, and even cesium, but rubidium is a bit expensive. Let me quickly pull up a picture of rubidium. Here's some rubidium in a sealed ampule, because if you left it in air, it would start to oxidize, even start to burn. Silvery gray. The atomic number 37. It's Rb rather than Ru because ruthenium was discovered first back in 1841. It wasn't until 1861 that Bunsen ended up discovering it. One of the methods that they used for discovering elements was to burn things and getting characteristic flames. And the flame test, characteristic color of flame for rubidium, is this ruby color. So there we go. We've got our rubidium, and here's a larger sample. Interesting is that average atomic weight is 85.5, made from a 85 isotope rubidium, and then 28% of this radioactive 87. But the radioactivity rate is pretty slow. It's a half-life of 49 billion years, so it's going to take a while for this radioactive 87 to eventually end up completely decaying, and then that'll lower our average atomic weight of rubidium. But let's go to what we're going to deal with. Is the question was to come up with the electron configuration for this. The standard method for coming with electron configuration is you can look it up, which I would do for transition metals because they get pretty tricky. There's a lot of exceptions to what you would expect. But you can sort of predict what it's going to be using the periodic table, and that's what we're going to use. We're going to start with a count up. We're going to add electrons, Aufbau if you like, and we'll see some patterns that are important, so it's worth doing this. We'll start, here, we'll start with filling in our first energy level, our 1s energy level, and here what I'll do is I'll pick an arrow. I'll get my arrow going, and I'll pick yellow. And this means we're going to get 2 electrons filling in our first energy level. Our first energy level, all it can handle is 2 electrons, 1, 2. And that is designated in terms of electron configuration with 1, first energy level, S, which stands for a type of subshell. And then it's got 2 electrons. That's what our subscript's all about, a 1s2. We've filled in 2 electrons. Now, as soon as we've filled in those 2 electrons here in the first energy level, we don't have any more room. First energy level, 1 subshell, 2 electrons, and that's it. So we're going to have to jump to a new energy level, which is the second row on this periodic table. And let me just use that. That's going to be, I'll use orange for this. I'll grab my arrow and pick a nice orange. We're going to be adding more electrons. Lithium and beryllium are our second energy level. The subshell involved, because our electron configurations have to show these subshells. They're important. They determine a lot of the chemistry. In fact, that's why we've got this shape on the periodic table. We've taken care of our 2 electrons, and that's it. We don't have any more room in the S subshell. So now we've got to start filling a different type of subshell, our P subshell, which can hold up to 6 electrons. So I then would say here we have our second energy level. Still, because they're still in the second energy level. The second energy level has 2 subshells. I mean, that makes sense. Second energy level 2, 2 subshells. We're going to have a total of 10 electrons, 8 of which are in the second energy level, 2 which are in the first energy level. These p orbitals that we have here, which I will show here, which there they are, sort of our p orbitals, are sort of unusual, and I want to bring up this. They have this sort of like dumbbell shape. If you have one electron in a p orbital, it will assume this entire figure 8 shape. That'll come in important later, especially in organic chemistry. And then if we have a second electron, it'll fill up this other figure 8 and this one. These are determined by quantum wave equations, which are really interesting, but they're just too complicated to figure out unless you've got some great computing power. But these are the shapes of our p subshell that we've just written here. Now, as soon as you complete a energy level, we have to neon, when we get to this, or at least we've gone to a noble gas, we can do what's referred to as an abbreviated electron configuration. We can assume, in fact, let me get my text going here, that italics and use a bracket, and E, that's going to stand for 1s2, 2s2, 2p6. I don't have to write all that out. That's going to be our abbreviation. So there we go. We've taken care of, and this is what I want to show. We did hydrogen to helium. Now we're going lithium all the way across to neon. Now notice, even though we're getting more electrons, here we have 3, 4, 5, and even in a p subshell with that weird shape, 6, 7, 8, 9, 10, the size of the atom gets smaller because of the protons in the center. I mean, these positive protons pull in on the electrons. We start with 152 for our radius, picometers, and we're down to 70, even though we have 8 more electrons, but they're drained in by these attractions of the protons. That makes these electrons hard to get out, because, I mean, they're close to the protons. Getting rid of a neon electron is not easy to do because it's so close to the nucleus. But let's keep on going, because we've got to get to sodium. Our next energy level is the third energy level, and I'll see if I can find a little pink arrow. Okay, I've got my pink arrow, and I'm going to be filling my sodium. Oh, that's, I guess, not a pink. that's almost a phenolphthalein color, magenta, I guess. We're dealing now with a third energy level. We're going to sodium, so we're going to do our 3s. Third energy level, s orbitals. And then we just keep on moving across. I get my arrow going, go through aluminum, silicon, phosphorus, sulfur, chlorine, another 8 electrons. So I'll have my 3 p's, third energy level, but now p subshells. We would end up having the complete electron configuration for element number 18, argon. Again, I could, if I was writing the electron configuration for argon, abbreviated, I would say, hey, I'm not going to bother with 1s2, 2s2, 2p6. I'm going to end up just putting down neon. And so we've got our abbreviated electron configuration there. And again, looking at our orbitals, we've just filled our 3p's. Now, there's something really interesting here. We've got some D's, but ignore them for right now. Ignore them. And this is the complication. That's why I chose this example. I'm going to jump right now up to the 4s, and I'm going to use a blue, I guess, for my arrow. Fourth energy level, I'm moving across. Now, again, with our sizes, now we went all the way out to argon from 186 picometers to 98. Again, more protons pulling in, and making a smaller and smaller atom. But now, zap, we're going to a new energy level with potassium, and we go from 98, this really, really small atom, to 227, more than double in terms of size to get to potassium. And that's our repetition. This is our periodic table. We do this and then do things periodically, again, over and over again. Now I'll just, of course, since we've filled this argon out, I can change my abbreviation to AR, and that'll take care of my 3s2, and this stands for the 18 electrons that are the 1s2, 2s2, and now I can build up to my 4s2, fourth row. I'm moving this here for a reason. I'm putting a space. Fourth energy level, 2 electrons. Now, here's where we get to something that you just have to know. And I'm going to pick up my color here again. The transition metals start filling the lower energy level 3Ds. The 3Ds aren't filled until you have a couple of electrons in the 4s. Just something that you have to remember. And it's easy enough to remember. You can say, hey, third energy level's got, some D. It's got 3 subshells. It should have a D here, but the D doesn't fill. The 4s does. There's enough repulsion down here to push these initial electrons up to the 4s. The 3D and 4s are really, really close together in terms of energy level. I mean, they flip back and forth a lot. So we're going to have to put these 3Ds, put them right here. You group all the energy levels together. And a lot of books, they'll have this 3D after the 4s2. That's a recipe for disaster. Don't do that. They're just, they've just pretty well been said, no, do this instead. And eventually, another 10 years, the textbooks will catch up with that. So this 3D is buried because it is lower. I mean, it is lower in energy. It's close. I mean, the 4s and 3D are really, really close together. But when you have ionization, when you take electrons off of things, you take them off the top energy level. If any of these transition metals ionize, lose an electron, they're not going to lose their 3D first. They're going to lose a 4s first. Now, sometimes things get a bit weird. Like chromium, which should be D1, D2, D3, D4, is really a D5. It takes 1 electron from a 4s. Copper does the same thing, and it'll be a 3D10, 4s1 for copper. But you don't have to worry about those exceptions in AP chemistry. In college, yes, but the transition metals, D subshells are so close to the next upper energy level that they swap places, and electrons move around, and you really have to look these up because there are so many exceptions. Half the transition metals don't follow the regular accounting rules that you'd expect. Sometimes you get a 4s1, sometimes you get a 4s2. Chemistry of the transition metals is very, very similar because they have the outer energy level being an S. And even in terms of size, you'll see that the transition metals don't change much in size. They're almost identical to some extent in terms. But we're going to go across all the way to krypton. And I'm going to pick up my blue arrow again because these are going to be our 4th energy level again. And I'm going to pick up this and make that 4p6, going all the way to krypton. Now, if I was doing the electron configuration that was abbreviated, I would write it argon up here. I would include the 3D after it, and then I would go to the 4p6. Here we go, paste. With the abbreviated electron configuration, you go to the noble gas before, argon, and then you write everything that comes after it. Rearrange it so that the D subshell, which is 1 energy level less just before these, because these Ds are going to be buried underneath in terms of energy, but we've got to get up to rubidium. That's just 1 more electron. I'm not even going to write it down. I'm just going to bring it up here and say this is our 5s1. Now, abbreviated, again, we pick up our noble gas that comes before it, krypton. So I'm going to change this to Kr. Look out, Superman. Krypton. That takes care of these guys. I'll cut that because krypton is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, all the way across. And we just have, this is a really nice abbreviation, 5s1. Here, 36 electrons, krypton. 1 more electron, rubidium. In fact, if they ask for an electron configuration that's abbreviated, well, that's so nice because you just pick up the noble gas before and don't worry about these guys buried underneath. The other, in this case, 36 electrons are taken care of by this krypton. We'll double check. Krypton 36 plus 1 electron. This little electron here, rubidium 37. We've made it. the electron configuration for rubidium, and you learn a few other things on top of it all. If you can handle rubidium, you can pretty much handle anything else. So sneak preview, we would then go 5s2, then 41, and who knows with these weird things, and then go back up to row 1, 2, 3, 4, 5 P's, getting up to xenon. Okay, electron configurations, that does it.